All right, Bill, take it away, sir. Oh,
All
real
right.
quick, let me introduce Bill Mueller. Sorry. I do some panel work for Bill. I've known him since I transferred to Davis as a junior. Bill has a long background in automation that I'm sure he can give you a quick breakdown on, but I've asked him to come in and talk about automated systems and ladder logic and give you much more knowledgeable and detailed base on that before we really get started. So Bill, take it away, sir.
Cool. Well, thanks. Yeah, I watched last week's class as well, so I tried to tailor this around it a little bit, but I definitely just threw some stuff together. We'll go through it around a little bit more systematically, but feel free to ask questions as we go and slow me down if I end up start talking too much. Especially around acronyms. There are going to be 1,000 acronyms that I won't even realize that I'm saying because I don't even see the acronyms anymore. So if I'm talking too fast or didn't explain something completely, make sure you end up saying something. So number one, why should you listen to me? Short answer is you shouldn't. I technically own a business now, so that makes me technically the man, and you should never listen to the man. But I have 16 years of experience doing this for a bunch of different industries, life sciences, biotech and pharma, but also food and beverages, material handling, that sort of thing. Technically, I'm an expert, but I know people that are way better at it than I am. But I've also trained over 20 interns into very successful careers. So I got a little bit of experience doing this. The biggest thing that I've seen in every training regimen is that they skip that PLCs are just a tool, just like a hammer or saw. And much like a hammer or saw, they're very good at being taught very quickly and making large objects into small objects, but you just need lots and lots of practice so that you can actually use it as the tool that it's supposed to be. In that regards, the last class you had was a good introduction into ladder logic. This one here, I want to give it just a little bit more fleshed out context for how it's done. So the agenda is just to give you where PLCs exist in industrial manufacturing, go over just a really quick review of what John went over with you guys last time. Start fleshing out a little bit more of the instructions because it sounds like you guys have all played with that click program and introduced what isn't obvious in the demonstration, but the fourth dimension, which is time, and playing with the PLC scan time. And that really unlocks all the potential of the PLC. Then looking through the click code, I spent some time with it. Generating new code is probably not the best thing for me to do, but they do offer a bunch of sample code on their website. So I can go through that, explain it, answer any questions that you guys might have on it. And depending on how fast I speak, there might be time for questions or me to tell one of my random stories. So starting right off, since you guys are from a very prestigious school, the Purdue model. I actually hate this thing, but I can't think of a better way to describe when people are talking about manufacturing control systems. It's a mile wide concept. But where we're living right now with this project is really at level 1, and the panel is probably living at level 0. But that only usually tells just a very short part of the story. The actual part where if you've been watching how it's made and that sort of thing, they're looking at all 3 of level 2, level 1, and level 0. Above that is actually how the plant gets designed. And from what I understand from dealing with other chemical engineers, your classes actually deal with this as one big whole, where they design the process, they end up sizing the tanks, doing all the math and stuff onto it. that whole process of when you guys build your facilities incorporates all of this. For this particular class, and from what I've seen so far, you guys are really just focusing on level 1 and 2. To remove some of the abstraction a little ways, this is another way to represent the same data. Up here, this is all the business services and stuff, but this is where you start getting all your reports, where you can, and I know this is hard to read, but you guys can pull down any Purdue model thing and it shows you 50 different ways. But it's just a way to segment it out and then have people that, there's people that their entire job is just one of these types of segments. What's kind of cool about what you guys are doing is you're actually covering 3 of these at the same time with that VFD and the controller and that sort of thing. This also gets closer to the plant floor and for specific processes. So like if you end up having an entire biotech processing line, these pieces down here at the 1 and 2 would be an individual bioreactor, bioinoculation skid, that sort of thing. Or if it was for food processing, it might be a mixer or it might be a extruder, that sort of thing. And for you guys that have really want to get into plant design, this is what it really looks like when you start breaking it out. So all 3 of these slides are the exact same thing, getting closer and closer to how real life goes. If you look really, really close down here at the bottom, you end up seeing this box here with a drive, controller, and I/O. This box here is where the panel you guys have built would live in this entire system that would be a plant floor. Kind of so, and I don't know why that just jumped. So when I'm saying it's a tool, it's for like the kind of work that I do, the PLC, the HMI, the drives, very small section of the overall whole, hugely important, hugely important. So what you guys are doing down here is going to support the rest of the facility. So diving into it a little bit deeper. There are a billion different names for all the same stuff that's out there. A lot of acronyms as well. The field controller, PLC, IED, RTU, controller, PAC. I probably only know 3 of these guys. The PLC, programmable logic controller, real-time unit, and process automation controller. These are what you guys are dealing with where your click is living right now. For your field devices, meters, sensors, valves, and switches, that's the push buttons, the indicator lights, and the VFD that you have in your panel. And if I saw the picture correctly, you have, can you see the right-hand side of the screen or is it blocked out?
Should be able to see it. I know in the very top right, there's going to be a blocked out section for the recording.
Oh, okay.
Be able to see it.
Let's zoom it out just a little bit and see if I can make it a little bit more visible. So the HMI is the human machine interface. That's where you're going to make all your screens and where you actually end up interfacing with everything that's beyond just the normal push buttons. As far as controllers go, there's a ton of them out there. Here's a picture of what your guys' should look like. And these ones are more what I deal with in my day-to-day life. These 3 processors here are different parts of the same family. They're all Allen Bradley controllers. This one has to do with safety and verification for like nuclear plants or highly sensitive wastewater type stuff. These are just general purpose, and these are for smaller scale projects. Siemens processors, they're around. A lot of the world's been sliced up by manufacturers. So Allen Bradley has most of North America. Siemens has most of Europe, European style programming. So depending on where your equipment comes in, you'll see one or the other. Programming it. So I know you guys are going down ladder. John touched on it just a little bit before, but there's many, many different ways to program a PLC. This example here comes from my development environment, and this particular one uses well, 4 different ways to program it. Structured text looks the most like some sort of C Java hybrid. It's pretty easy. New computer science people pick it up really fast. It's all right. It's got its own place. Doing iterative stuff like what you're seeing here is really where its benefit is from. This one in the upper right, that's function blocks. And a lot of people like it, and I just can't handle it because of all the wires trying to trace it out. When you end up having this be like 500 units, trying to figure out how everything goes together is really difficult, but certain industries really like it. Each of these blocks has a single function. You end up drawing the lines for where the inputs come in and outputs go out the other side, and you can really see step by step how data flows through the system. Ladder logic, that's this guy here, and that's what you guys did last week. Ladder logic was originally done to make it easy for old-time electricians to start programming these new fanciful programming devices. When I first started, you ran into a lot of panels that were just used relay logic. The exact same contacts and coil logic that you see here, they had entire panels made of them. What's even cooler is in places where they do hazardous stuff, where there's powders or solvents, they used to do them with pneumatic valves the same way. So you would end up having big panels that were done just like relay logic, but it was all pneumatic valves and it was the trace of the air that came through. So this is intended for fast debugging and also for handing it to the maintenance people on the floor. And down here on the bottom right, I had to dig deep to find an example of this, but sequential flowcharts. I don't know anybody that programs in them, but I hear it's really popular in Europe. So sorry, I can't help you too much on that one. This is straight from one of the projects that we looked at before, and it is just the further extension of what you guys did last week. It gets really crazy when you end up having much larger systems about all the different permissives that end up happening on here. Even though it's using a very simple idea of normally open, normally closed context, you can actually make some really interesting style programs that are very complex in nature to solve high speed and very complex problems, like running a bioreactor or doing a multi-lane shipping type system. And most of these components you guys saw last week. Just regular contacts, regular coils, and a timer. I mean, it's not rocket science, but this portion right here at the bottom is where we're going to get to today. You should already understand this top part, what it's saying. Down here is really where we're going to get to by the end of the day.
So Bill, real quick, can you just talk about, in context of a big plant, why are there so many contacts on that first row? Like, what does that mean, you know, in context of an operation?
Okay. So there's the real answer and then context with the click processor. So if we did it within the context of what this is actually intended for, this is for a fan system that ends up allowing constant flow of some sort of fluid or air. And this is the permission to run. So say if this is for a pump that's going to be filling a tank, or it's a exhaust system for a solvent coating room or something like that, each of these contacts would be set up to one of the safety systems that are out in the field. So you may have, like here, first check to see if the pump is able to be controlled by the system, which would put it in automatic mode. If it's in manual mode, we don't even want to try. Here we end up taking a look to make sure that first the motor's not in overload. Motors, when they've been running in a stalled condition, or there's some other problem with it, tend to heat up really bad, and they'll flip a thermal switch. That's what this guy is. Very large DC motors have trouble with vibration. So if you have a really big torque load on a shaft, there's a tolerance for which that shaft can be vibrating as it's running. If it starts vibrating too much, you can end up destroying the motor itself, the equipment attached to it, and the poor operator that's standing next to it would probably end up dying if it's of significant size. And all these other ones are process specific safety stuff. So if any one of those safety components end up coming in wrong, then you don't want to be able to allow that pump to run. The other big important piece on here is that, I'm going to try zooming in just a little bit so you guys can see this. Normally open versus normally closed. You covered it before. The normally open contact here turns to a 1 or is energized when it's closed. These guys here are normally closed contacts and are energized when they're opened. The reason for that is that for really, really important safety components like the motor fail, vibration, low pressure, high pressure, using a normally closed like this guy would tell you if a wire fell off. So if you end up having the system that if it's non-fail-safe type system, you want to make sure that even in a failure condition, if somebody's out digging a trench someplace and cuts a wire, you want to have it assume that it's in a fault condition. So selecting these guys was really important. They probably have a version of them out there that would be 1 means good. But in this case here, they're using them as a fail-safe condition. And it's all process specific. I don't know if I explained that great, but that's the reason for all these. And actually, this timer is also another safety condition as well. When you have these very large VFDs, they take a lot of current. And when you start up a pump, a 3-phase pump or even a 2-phase pump, they use big contactors. They look just like relays. And the really big ones, they're like 2 fists that when you turn them on, they'll clink ka-chunka together to make the electric current go through. And then there's a big spring that when you turn them off, it actually has to ka-chunka pull them apart. And that's because there's so much voltage on between it. You need to have that big surface area and spring assist to be able to pull it apart without them welding together. The timer that you're seeing here is intended so that you can't just go up there and go start, stop, start, stop, start, stop, because that thing will be just going ka-chunka, 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 ka-chunka until it welds itself together. So this is also a part of the safety circuit. So anyways, that's what we're looking at there. Yeah, that's process specific. When you guys go to develop your own, you'll dial those in yourself. So I made a reference to the 4th dimension. And this is one of the parts that's really hard for when you're first start programming to end up seeing. And it requires an innate feeling of how the program executes. So every rung ends up executing from left to right, top to bottom. Seems very easy to understand at first, but later when we get down there, you'll see that because of this, we can end up doing some really fancy programming that's non-intuitive. Every time the PLC code goes from the top of the program to the bottom of the program, that's 1 scan. And the PLC, when it's on scan, just keeps on ripping through each of the rungs in the same order. And I copied this from somewhere else. It should be obvious that a PLC could complete many scans in a single second. But example of this would be is that like out of those processors we saw above, the Allen Bradley stuff executes between 10 milliseconds and about 50 nanoseconds for a scan. I didn't look up what your click was, but I would imagine it's probably between 20 and 30 milliseconds for the type of processing I saw it doing. So review. Normally open contact, normally closed contact. These are modeled right off of the electrical drawings for what a relay looks like. A real relay has a round coil. Real relay has a contact that looks just like that. So if you're to wire up a relay, these are the symbols you'd see on it. So using that, we can end up coming up with some Boolean logic. So it's regular Boolean logic, we end up having just a regular OR gate between these two guys. So if input 10 is on, coil turns on. If discrete output 8's on, coil's on. You can either have one of these two or both of them on, and you'll get a 1 out of this logic. Pretty straightforward. In contrast, if you put them in the same line together, this is the same as doing a logical AND function. So having just input 10 or just input 11 isn't sufficient enough to pass electricity through. The important part on here is that by switching the type from a normally open to a normally closed contact, you can change it so that you have somebody pushing in the push button for input 10 and somebody releasing the input for number 11 to pass electricity. And you guys used a set of lights, but realistically, you can use the same thing for controlling a motor. If you want to start the motor, if you use just the straight coils, like in the example from last week, you press start. As long as you're holding it down, the motor will be jogging. And if you want it to stop, you click stop, it stops. So that code looks just like this. So if we end up having either one of these be true, the motor will start. And it'll continue to run even after you let go of the start button until somebody presses the stop button. I'm going to go into a little detail on this later, but this is called a latch. And this is one of the primary things that a PLC is good at. And this only works because of the scan and playing with the fourth dimension. So we'll get to that here down at the bottom. So any questions on the review stuff so far? Cool. So these are, well, except for the sequencers, are going to be the main components I'm going to cover for what you need in your toolbox when you're programming a PLC. These use those primary data type objects like the normally open, normally closed, timers, that sort of thing that's available to you, but it ends up putting them in a certain way that you're going to see repeated over and over again, that with practice you'll see where their application is in a system. So the first one and the easiest one to do is a latch. And this looks a lot like that motor control. And I didn't number these really quick because I spent like 5 minutes putting these together. But what this is it's the same rung 3 different times. And it's the same rung at 3 different periods of time. So when you end up finding this top rung, it is at its default bench state. A little green box on there means that it's passing electricity. Nothing on there means it's not passing electricity. So if you ended up pressing my latch request bit, it would pass electricity through and turn on the latch bit. Pretty straightforward here. So this is at bench. This is after you press the my latch bit. As soon as it comes through, this guy will turn on. The unlatch request is not there. Turns on the latch bit. On the next scan through, this guy comes off, this guy stays on, and it maintains this latch. You guys see how that happens? So when it first comes on, only one of these legs are true. When you let go of my request, like say you let off on the push button, this latch bit stays on and we can end up using it. So if we ended up looking at it, if time is going to the right. Request is 0, turns to a 1. That's exactly when we see the latch bit turns on. When you release the button, request goes back to 0, but the latch button stays on for basically ever. You probably can see already how this is going to end up changing. I guess I didn't put in that slide. So if you ended up having the unlatched button, say this was the stopped button, right here, you would see the latch break and it would be off forever. So this sets the latch, this unlatches the latch. And you're going to use it for all kinds of different stuff. A lot of it with being catching pulses and transient signals in general. One-shots. One-shots are my particular pet peeve. I wrote an entire LinkedIn article of why one-shots are a bunch of crap and why you should do it my way. But one-shots are really useful for non-obvious reasons. One-shots means that you'll end up having a bit on for exactly one PLC scan. So if you're doing mathematical functions, if you're doing resets, if you're doing something, it's always nice to be able to churn a long pulse into a single pulse for one PLC scan. And there's examples down further. But the way this works is, again, 100% due to the way the scan works. So left, right, up, down. When we sit here at bench state, my request is off. So electricity is not passed across here. Request one-shot isn't there. One-shot working is not. On the very next scan, my request turns on. That's the edge right here. When it comes through, one-shot working is still not on yet. So we can go ahead and turn on one-shot for that. We finish up, cycle around the scan, come back to the top. My request is still on. But now one-shot working is now on. So that means we don't no longer have the one-shot anymore. So as long as my request is on, we're only going to get one scan of this guy. So it looks just like this. On the leading edge of request, we get one pulse out of it. It's very useful. Well, this is important to build off of for the next section. Timers. Timers are primary data types that the timers in this case work the same way as that they work on the click as well. At their rest state, you end up giving it a number that it's going to count up to. In this case, this is done in milliseconds. So 3,000 milliseconds is 3 seconds. And what we're trying to do is delay this request bit by 3 seconds. The way we end up doing that is as soon as my request comes on, timer starts timing. These little dingles on the end here are the output bits from there. While it's enabled, accumulator's counting up to 3,000. Done bits doesn't turn on until it reaches that time. Here's the next one. We've reached 3,000. Done bits on. Done bits on here. So now we end up having the delay sequence. So this little piece of logic just takes a pulse and shifts it over 3 seconds. So you can either shift a pulse for 3 seconds. We can hold it for 3 seconds. There's all kinds of stuff we can do. It seems rudimentary, but it's used all over the place. Now, taking that one step further where we're actually using the done bit for good instead of evil. The only difference between this set of logic and the logic that was above is that we moved the timer done bit in line with the timer itself. So when my request comes in, the timer's not done, counts up to 3,000 seconds. Once we're at 3,000 seconds, timer bit comes on, the enable bit drops from here, resetting the accumulator. We get a pulse, a one-shot pulse for one scan, because the next time we come through, request is on, timer is no longer done, counter starts going. So the pulse trains ends up looking like this. We press the request button here. We wait our original 3 seconds, just like we had. Sorry, throat getting dry. We have our 3 seconds here till the first edge. But after one scan, timer resets, so we end up with the same thing. So for whatever reason in which you would need it, you can end up sending a set of 1 scan pulses this way. Excuse me. And you never know when you're going to need something stupid like this. I've used it a lot for this. Actually, the most recent one that we used that was doing this way is for doing a video game in a PLC. So we needed a game clock to synchronize user inputs with, and this was exactly the way that we did it. But it's manipulating the scan time, the left to right, up to down, to make this work that way. Counters are intuitive. It's basically just an adder. There's count ups and count downs and all kinds of other random ones out there. But when you first use this, it's a little non-intuitive. If you wired it up just like this, where you have the counter on one side, we're going to count up to 3 and then say we're done. If you put one impulse, this was a push button, you push that button once, you would think it would only count once. But in reality, what it does is that every single scan, it's going to increment once. So as for as long as the request is up, it's just going to keep counting each time through. The important thing to pull out of this is that this is one of those examples where if we ended up having a one-shot in here, we can end up for count every single time that pulse comes in and synchronize it with the PLC scan. The other thing to catch out of this is the done bit. Just like the timer, once the accumulator hits whatever your preset was, you'll get the counter done bit as well. So request comes in, counts 3 PLC scans, and then you get 1 bit here. How can we use that for our help? Here's that one shot. This is the one shot we did right before. We can end up saying, here's my request, turn it into a one shot, use the one shot to increment, do the counter. So request comes in, comes up, is held for longer than 1 scan, but the counter only clicks up, chink, chink. When you release the my counter here, I did this wrong. So this little slice should actually be on the leading edge, not on the falling edge. So this one's done right, and that one's done wrong. But each time you press the button, it'll count 3 pulses, and then once you get to the 3 pulse, there you go. But this looks like garbage, and if you ended up having 1,000 valves or whatever it is to do, it's a little bit complex. So you can end up rearranging it so that you can use that same one-shot logic, and instead of having an output in the middle, go my request this way, and it'll count up the same way, except again, this is on the wrong thing. So building a one-shot this way, hold on one second, through the front door. So yeah, so you can start building it up this way using that timer piece. Messing with it even further, counters also have a reset bit, just like the timers. So if for whatever application you're doing, you want a repeating waveform that looks like this, you can use that counter done bit to trigger the my counter reset. So as the request comes in, my counter just starts, the accumulator starts giving you this waveform generated like that. Kind of cool at the other side is that you also get these one shots for the done bit. So as soon as it hits done, drops off, comes back up. Again, I don't know why you would use this, but the most likely way you would use this is some sort of sequencer type deal, or whatever your application needs. Forgot I did this. So this is for the rudimentary sequencer. Say you end up having something simple like your coffee pot. It really only does like a couple steps, or like a traffic light or something like that. You basically have this guy free running, giving us our pulses here, but we end up using the comparison to end up selecting the steps. So as this guy keeps counting up and down from 0, 1, 2, 3, if we're less than 1, do step 1. If we're at step 2, do step 2. If you're at step 3, do step 3, and then reset yourself. So here, if you ended up having whatever your sequence is, you can have discrete control over your sequences. This one's a little not the smartest thing, because basically your sequence is stepping through at the speed of the PLC scan. So if we go back and add our timer into it, we can end up now stretching out each of the steps. So the timer runs when it's not done. As soon as it hits the accumulator, resets itself. That single pulse that we saw from above is what's being fed into the counter. So each counter time it rolls through, steps up. Each step up, we do whichever step we're currently on. So this builds up from what we started with before, where there's no latch in this one, but we're definitely using a one-shot right here. Using the timer, using the counter, and using your discrete steps to pull it all out. If you were handed to this thinking, hey, how does this execute by itself? It's kind of hard to see until you really try to map it out with some sort of either waveform or some sort of table to show you how everything changes over time. It's a little bit easier to go. If you tried this in a modern day programming language like Python or C or VBA or whatever your poison is, it wouldn't work the same way because it doesn't leverage the scan of the PLC the same way. And then these are just nice, easy little ones to add extra for the end. Data transfers. There's really two ways to end up moving them around. A move just takes two data types of like type, moves it from one to another. So when you press my request, changes my value down to my target. Every PLC has it, some way to do it. Thing is that the types have to be the same for both. If you want a type that's more complex, say like a string or some object you made on your own, an array maybe, you have to use a different type of transfer, and that's called a copy. And there's lots of different ways to do this, but say you end up having a complex object called my object. Here's the definition of my object here. So for every one my object, you're actually getting built into it an index value, a string name, a floating point X position, and a floating point Y position. If you want to move that object into the other one, you can't use move directly because it only knows primitive types. Copy will allow you to move multiple of those objects into the other guy. Again, highly specific on your application. Math functions. I picked easy ones because that was what was in the click. So add, subtract, multiply. These are just regular ladder blocks. You can see how that all ends up working. I put it as a one shot here because otherwise, if you did the my request by itself, every scan, it would just keep adding another value or subtracting another value or multiply another value. If you didn't range check any of them, like I have here, within probably about 30 seconds, you'd probably fault the processor as you overloaded the data type of whatever we're doing here. But in this case, only fires once. Very cool. And click examples. So doing a time check, we got about 10 minutes left. So how about we open it up for questions over the stuff we just went through, because that was a dense wall of text. Sweet.
So yeah, you know my pain. So I just want to jump in here and say that the Bill is giving examples from Alan Bradley or Rockwell programming suite. So all of the operations that he went over, I believe we can do in the Click software. It just looks a little bit different. So for example, on these math functions, instead of having discrete add, subtract, multiply, there's just a math block, and you select what math it does inside of that block.
Yeah, and that was intentional. The thing was that I was having a hard time figuring out how to actually implement it in there. So
Sure.
That's when I went through the examples. So, sure. So we can either rip through the examples, or we can go right into story time. We can go into question time. I'm down for any way you guys want to do it.
Let's put it to a vote. What do you guys want to do? I'm gonna have Bill rip through some code real quick.
Yeah, here, I'll switch. Go for it. So I didn't really trust this software a ton, so I installed it in a virtual machine. So let me just restore it real quick. You guys can see my virtual machine booting up, right?
Yeah.
Yes, we can.
Okay. So on the website, there was
So while Bill is doing this, I just want to say, guys, like he said, this is some dense material, and I don't think anybody would really expect you to understand 100% of what he just covered without going through it. So that's what we're doing this quarter, is we're going to try to work on examples of what he's talked about. The huge advantage of having Bill present is that I'm also learning along with you guys and realize some things that we can definitely improve in some of the code we've already written, as well as implementing some of the things he's covered going forwards.
Yeah, and it's just another tool in your box, and where you get any good at this is just by applying it over and over again so that you can figure out which is the right tool to do it. And yeah. So this first one, so all these examples came from the website, the Click website, and they came in sample code so that you can download it and see which tool is the best way to go with. This was MISC number 4, which is trying to tell us what? Oh, displaying the counter values. Wait an hour. Okay. So here we end up having our timer that ends up being set. What's kind of nifty about this one here is that instead of using full-on numbers, absolute values here, they're storing these values inside data registers. So the set point is the same as what you saw before. It was the preset is stored in data register 1400. The current value of it is being stored in TD01. So as soon as you end up giving it a start command and it's not done yet, this timer starts ripping through, starts counting over and over again. Here you can end up seeing that it's got a one shot in there. They use the instruction that I hate with burning hellfire, but they're using it here. And then they're using this guy to copy over the preset and doing the math to subtract it on out. So what this will do is that they only have the counter that counts up, I believe. And so what they're trying to do is show a countdown timer. So say if you are doing a transfer of some sort, some fluid from one vessel to another, it doesn't help them at all to know that the transfer has been happening for 20 seconds. What they're really interested in is when they have to start paying attention to it again. So say the transfer takes 30 seconds, having a counter that goes 30, 29, 28, they can ignore it until they see it's being 5, 4, 3 kind of thing. So they're using the copy command into the preset and then doing a math block so that they can end up displaying on your HMI, how much time is actually being left. It's kind of clever way to do it. And that's based off the timer. Here's where they do it based on the counter. Here they end up having, instead of a timer doing it, they have a counter doing it. So if you press X2, counter counts up, keeps counting up. They end up grabbing that bit. Once your counter is complete, copy the values over. That's what this guy's doing. And then do the same thing for the math. I didn't read the comments too much, but when you would use a counter in this way, instead of using this counter increment bit, using the timer done, you can end up using the timer, have the timer rip through seconds, and then use this counter to count minutes based on it. So then you would set this counter preset to 60. So after 60 seconds goes by, the counter counts up to 1. You can now have an easy way to display the minutes. And then feed this guy into another one that does hours and days and all the other good stuff. So this is pretty complex. To start with, shows the counter and the timer functions as similar. There's only one time dependency on here, and it's with that one shot that they're using up at above. So, oh, and you have to make sure you use the end. That is infuriating that you have to do that. But remember the end, because it doesn't tell you why it's failing to compile if you forget it.
Yeah, I'm with Bill on that. It drives me nuts. One thing I wanted to point out, it's super important, and maybe you didn't pick up on it. When he's talked about how all these timer and counter values are stored in memory locations, that's very different from how Alan Bradley does it. So in the examples previous, he was showing you those math values or whatever, those are basically discretely stored in that function, whereas here, these are stored somewhere in memory, and you can externally access those memory points at any time. So if you want to dynamically access and change that counter value, you can. So for example, you could have somebody go in and type a value on your HMI and change what that preset timer value is.
Yep. Yeah, it's a big deal. So, and it looks like we've just about ran out of time. So I only got through one of these examples. Hopefully you guys ended up finding this somewhat interesting. Realistically, what it is you guys are going to be working on your own programs and try to remember what that dude told you about to solve this problem. But yeah.
That's why we record these, Bill.
Oh, yeah, I can't wait. They were eagerly awaiting to watch this back at the office. So.
Oh, yeah. Hi, Jacob. Hi, Marie. You're going to be YouTube famous, Bill.
In my own little corner of the internet. So.
Okay.
Cool.
So any questions from anybody? We got a couple minutes left.
Well, how about this?
Question, actually. So the 7, I don't know what to call them, like methods or configuration, the latched and one-shot things. Mm-hmm. So we don't have some of those in the Click software, it looks like, and then the Click software has some other ones like drum and shift or something. Are those specific to the software that you're using, or are they universal?
Yeah. No. So you're right. You're everything you're saying is right. So what I did is I picked so the Click, going back to the 7 that I ended up showing before, those all can be implemented inside the Click processor. Sort of similarly, the only real difference is that in the examples that I gave, the normally closed, normally open contexts were registers, but for binary. Those binary registers don't exist in the Click software. So if you want to use like the working one shot and all that, you actually have to assign that to IO that you're not using to make it work. And that's where I was getting hung up with trying to show examples specific to the Click. So those same foundational pieces though, latches, one shots, that sort of piece on there, you definitely would use those as different tools inside there. the second part of your question, where you end up seeing like drum, like FLL, Phil, and a couple of the other ones, those are processor specific ones. So like an automation direct processor, you're buying that unit because it's been custom made for whatever industry that it's done with. And the best thing that I can tell that it's for is for like conveyor control. So when you end up designing a conveyor system, if you like the large conveyors that you end up seeing for like bottling plants, or for like in Amazon for the original feed, they're called accumulation conveyors. So you'll have a section of conveyor, but it's actually divided up into multiple little sections on there. And each section has a solenoid that basically just pops up a little thing to block the box or the bottle or whatever it is, so that you can pull gaps and all that other kind of stuff. In that kind of a process, what you're doing is you're really trying to track where a bottle is on the conveyor, and then do it a discrete output for places to end up being stopped. The logic that's in that automation direct is tailor-made for that kind of stuff. But if you were to try to use that for, say, like controlling a bioreactor or like a petroleum distillery stack or something like that, it doesn't allow you enough computational or control to be able to handle all the different conditions of separating out those. Or if you're taking, say, a cascaded PID loop or something like that, that's not the tool for the job. But and Allen Bradley can do that. Siemens can do that. But if you try taking an Allen Bradley or Siemens to do a conveyor system, you're basically buying a $5,000 controller to do what this $300 controller is meant for. And it can do it better than them because they have, it's been highly optimized for that particular service.
Uh-huh. Okay.
Yeah.
Thank you.
Mm-hmm. Cool. That was easy enough.
Well, thanks, Bill. I really appreciate your time here, and
No sweat.
hopefully you helped clarify the muddy waters a little bit.
Yeah, well, we'll see. I can't wait. Good luck with your guys' process. If you guys have any questions, John can share my email with you, and you guys can hit me up direct. All right.
Okay. Do you mind sharing these slides?
Yeah, as long as you don't hold me up to that one error that I ended up finding. I'll email it to you, and you can distribute it as you see fit.
Absolutely. Thanks again, Bill.
Cool. All right.
Thanks
Take it easy,
everybody
guys.
for being here.
Thank you, Bill.
Thanks.